So det som är
Good morning. So now we start a new topic, which is more or less some overlaps with the previous metric spaces, but not that much. So first, I want to talk about the notion of sequences, but of course, we want to generalize this idea to sequences in metric spaces. Okay. So what was a sequence? You remember we had some definition of a sequence back then. I mean, lesson 1 or 2, I don't remember. So what is a sequence? It's a function whose domain is the set of natural numbers, and its codomain so far is the set of real numbers. So for example, we can say that I have a sequence which goes from n to r so far, yes? And then it was common, for example, if n is a natural number, it is common when you are talking about sequences, instead of using the normal notation of functions, and instead of writing p acting on n, you remember we denote this simply by p sub n. And then it makes us, this notation is comfortable because we can imagine a sequence as a list of numbers. Infinitely many of them are there. So what matters in a list is that order matters. I am not allowed to interchange. If I interchange, I am actually having a new sequence which is different from the previous one. And repetition is also allowed. In your previous courses, probably you're familiar, for example, in calculus, a sequence was given to you and then you were supposed to find its limit. So it means that in mathematics, what we care about is this eventual behavior of a sequence. So how this sequence behaves eventually. Eventually means after one point onward. Okay? For example, you know that in calculus, one of the things we were interested in is the notion of convergence. If you haven't heard of this word, it means find a limit. If the limit exists, you say that the sequence converges. What does it mean? Intuitively, a sequence converges to a number. It means that eventually those numbers gather around the limit. Yes? Gather around means what? Means getting close to that limit. Okay. So far, before studying metric spaces, R was the only probably, Euclidean spaces were the only ones that we can talk about the notion of getting close to distance. But now when we have the notion of a metric space, we can make there is nothing to prevent us about our imagination, so that we can talk about sequences in any set in which the notion of distance makes sense. Because if the notion of the distance makes sense in the codomain, then I can talk about points becoming close to one another. Okay, so that's it. So I just want to extend this to a metric space. Okay, so this is one particular metric space. Do you remember what is the standard metric there? Is the absolute value metric. But now, so if I want to discuss about the new concept, instead of just talking about the set of real numbers, let me concentrate on I have a metric space. A metric space. And then I have a function p, again with domain n, but the codomain is this x. Be careful, by the way, this x is an abstract set. What we know about this set is that it is equipped with a metric, so that we can measure the distance between different points in that metric space. So this is called a sequence. A sequence in X. This was called a sequence in R, but because R has a name, we usually call it a real sequence. Okay? But in this case, there is no particular name for a generic metric space. We say that any function of this form is a sequence in X. Again, nothing prevents us from imagining this sequence as a list, but not a list of numbers this time. List of points in that metric space. So if I want to write this, imagine this, it will be p sub 1, p sub 2, p sub 3, etc., p sub n, which is called the nth term, and the sequence continues. By the way, a sequence automatically means infinite, a list of infinite terms. Why? Because we have to assign one element from my metric space to every natural number, and because the natural numbers are infinite, this list is always infinite. So in the usual sense, when you learned about sequences in calculus, this list are list of numbers. But now if I am working in metric space, this list are a list of elements from my metric space. If my metric space is composed of numbers, this is still a sequence of numbers. But if they are not numbers, these are not numbers, okay? Is that understandable? So if you want to see this, so a metric space, X, so this is a sequence I define, and by the way, that's a notation, so it's good to know. So in the book, I don't know, for some reason this notation is used. I don't like this notation, because usually we use curly brackets for the case that we have a set, and in a set we cannot repeat elements. If we rearrange them, that's the same set. So this, I don't like it. This is why in most books usually they use this notation. Okay, or probably you can write this as well. But at least you can see that by putting just normal parentheses around that, you can see that the order matters. Okay. And then one more thing. What I can do, I can open a set. Now a set. This is a sequence. I denote it like this. Now I can open a set and do what? Put these points in this set. But when I want to put the points in this set, because of the notion of set, if something is repeated, I just write it once. Okay? So Pn, n belongs to n. This is different from my sequence. Okay? This is called the range of my sequence, or the set of points of the sequence. Okay? So that's called the range, which is of course a subset of your metric space. Okay. So let us now, if you have any questions, please interrupt me. So these examples are so simple. I just want to show you the slides, yes? So most of the time, again, we work with sequences of numbers, okay? But that is not an obligation anymore. But most of the time, the sequences are like that. So for example, this sequence that I have defined here, P sub n is 1 if n is odd, is 0 if n is even, okay? So that is the correct way, a formal definition of a sequence, so I have to define it as a function. But for us, it is easier to see this list. So do you agree that that list represents that sequence? And if I ask you what the range is not infinite. It consists of only two numbers in this case, 0 and 1. So that's the difference between the range of a sequence and the sequence itself. Okay? And the next one, the sequence of reciprocals of natural numbers. Yes? So these are sequences of real numbers again this time. Yes? And this one is probably another sequence that usually in calculus courses you don't face them. So this is also a sequence. Let me explain it here for you. So here, what I am doing here, this is 6.4. So the sequence that I have defined, my metric space is R squared. When I don't talk about what metric I am working in, it means this is the Euclidean metric. So what was the Euclidean metric, do you remember? So if I have 2 points there, so let us say x1 and x2, and y1 and y2, I have chosen it from R squared, then this is the Euclidean metric. The difference between x coordinates squared plus the difference between y coordinates squared, yes? That's the metric. So whenever I say that this is R squared without mentioning the metric, I am working with the Euclidean metric. And hopefully you see that this Pn, I have defined it in that way, for example. This is a sequence. Why is that a sequence? Because it is a function from R squared, from n to R squared. Any n that I give you, you don't give me just a simple number. You give me an ordered pair. For example, if I give you 1, you give me P1. But what is P1? P1 is 1 over 1 minus 1 over 1. And if I give you 2, you give me another ordered pair. So you give me 1 over 2 and 1 over 2. Okay? So if I want to list the elements of my sequence now, the first element is not just a single number itself. The first element is an ordered pair. The second element is another ordered pair. The third element is what? 1/3 minus 1/3, yes? And then I do not have a list of numbers, I have a list of ordered pairs. So that's the difference. If you go to a metric space, the notion of terms will be more generic. Understandable? So for example, I can talk about the limit of this sequence of ordered pairs in the future, okay? Okay, so now let us go to the next one. Okay, this is the notion of the convergence of a sequence in a metric space. Okay, so let me define it here for you on the board. You can also see the slides. So 6.5. So let us say that I have a metric space, okay, and I have a sequence in my metric space. And then I want to say, what is the meaning of this sequence be convergent? We say that this sequence is convergent if I can find a P around that. So P sub n is said to be convergent if there exists a P in X such that for all epsilon greater than 0, there exists a natural number in N such that if N is greater than or equal to N, then this implies that the distance between Pn's and this P is less than given epsilon. Okay, and if that is the case, I usually say that Pn goes to P as n goes to infinity, or we simply say that the limit of Pn n goes to infinity is P, and I don't even need to write infinity, I just can write just simply an n there. Okay, so this is the formal definition, but I want you to see this slide as well. So let X and D be a metric space, let P sub n be a sequence in X, and let P belongs to X. We say that this sequence P sub n converges to P if for every epsilon greater than 0, there exists a natural number n in the natural number capital N such that the distance between Pn and P becomes smaller than that epsilon if n is greater than or equal to n. If this does not happen, we say that a Pn does not converge to P, and if it does not happen for every P in the metric space, we say that it is divergent. Okay? So what does this mean? Let us unpack the different parts of this definition. I have written it here for you. So what is the meaning of this dP sub n P less than epsilon? What is the meaning of this symbol? It means the distance between Pn and P is less than a given number epsilon. This is clear. So it says that the term P sub n lies within distance epsilon of the point P. Thus, epsilon specifies how close we want the terms to be to P. Okay? So the phrase for every epsilon that you see here, for every epsilon greater than 0, says that no matter how small a positive distance we pick, the sequence must eventually get that close to P. Okay, might be, I think it's easier to explain this here for you. I mean, so let me explain it here on the board. So let us say that I have a metric space. You know, drawing a metric space is hard. Do you know why? Because the whole metric space is open. It's closed and open, yeah? So I don't know how to draw it, but yeah, so might be something like that I draw it. I know it is wrong because usually this means that this is closed, but simultaneously the metric space is open and closed, if you remember. Anyway, this is your X. And then what do I have? I have a sequence. Okay, I have a sequence, for example, this is P1, this is P2, and then I have a point P there in X. What do I mean by this sequence converge to P? Okay, this means that if you consider a positive epsilon, no matter how small it is, and you consider the neighborhood with center P and radius epsilon around that, eventually, this is important, eventually all the points of the sequence will lie inside this neighborhood. Okay, no matter how small epsilon is. So might be epsilon is so big that it contains all the terms. But even if you make the epsilon smaller, some of them will be left outside, but all infinitely many of them will be inside. Okay? And it doesn't matter how I am making this epsilon smaller. So in this picture, my epsilon is this much. If I make this epsilon smaller, and still infinitely many of them are inside, finitely many of them are outside, and if I make the epsilon even smaller, that this will happen, then I would say that this sequence converges to P. Okay? So convergence means that a sequence converges to a point if for every epsilon around that point, no matter how positive, how small this epsilon is, from some point onward, all the terms of the sequence will be there. And that's exactly this means that. This means that any epsilon that you choose, you can always find a natural number so that if the number of term is greater than or equal to this number, the distance from all pn's to that fixed p is less than epsilon. Understandable? So that's the meaning. Any questions? Okay, so for example, this slide is about, because this Euclidean metric spaces are one of the most important metric spaces, it's always good to write this for Euclidean spaces as well, so that you have, of course, this is the most general one. You can always rely on this definition, but let us first write this definition. Imagining that X is R. Then you rewrite this definition for me. So we say that Pn goes to P. P is an element in R. If what happens? If for every epsilon greater than 0, there exists a natural number such that what happens? Such that if n is greater than or equal to n, this implies what happens? The distance between Pn and P becomes less than epsilon. But because here I am considering a special case X is equal to R, instead of this I am allowed to write absolute value of Pn minus P less than epsilon. Okay? So this is exactly that definition. This is the general definition. That is a particular definition in which X is equal to R. Okay, so this one I want to do rigorously. So we want a very simple sequence is given to you. A sub n is given to be 1 over n. We want to show that this sequence converges to 0 in R with the usual metric. Okay. In calculus course, this is a very simple task. They ask you to find the limit, and then you say that, okay, I want to calculate the limit of this sequence, n goes to infinity, and you already know the answer is 0, and that was good for the calculus. But here we want to do some epsilon proof for that. So we want to prove it from definition. Okay? So this is example 6.8. And I want you to learn this. Okay? We want to prove this one is happening. Okay? So we want to prove that this sequence goes to 0. This is the question. The way you write it is like this. So I would say let epsilon greater than 0 be given. We prove that there is a natural number n such that what happens? Absolute value of my sequence 1 over n minus its limit is less than epsilon whenever, can you fill it up? Whenever what? I want to show that for every epsilon greater than 0, you can always guarantee the existence of a natural number so that the distance of the sequence terms from that limit becomes less than epsilon, provided that I am allowed to make n greater than or equal to n. Yes? So whenever n is greater than or equal to, yes? Of course, this problem is so simple, it seems a little bit strange, but can you say why? Why can I always do that? So my advice for you is to write, so this is the what we want to do. So let me write it with a different color. So this is a scratch paper. So you want to fine-tune this n, but this n should be natural. So that whenever this happens, this automatically happens. Okay? So this is a scratch paper work. For example, if this number is 2, if epsilon is 2, what do you choose for n? You want to make absolute, by the way, absolute value is you don't need it because 1 over n is positive, so you want to make it less than 2. Okay, can I choose n to be 1? Yes? Everything I can choose, yes? Any number I can choose, because if I choose 1, if n is greater than or equal to 1, this is guaranteed. Yes? If I choose 3, 2, 3, anything will make this smaller than 2. So if epsilon is 2, this problem is trivial because any choice of n will work. But if I make epsilon to be 1 over 5, for example, still I can fine-tune this question mark, but this question mark is different from the question, the answer to the previous case. In the previous case, you could choose any number that you like, any natural number that you like. But if I change my epsilon to 1/5, you cannot say still n is 1. Because if n is greater than or equal to 1, there is no guarantee that 1 over n is less than 1 over 5. It might be true or might be false, but I want guarantee. Yes, do you understand what's going on? So my question for you is that, for example, if I have this scenario and I want to make it 1 over n less than 1 over 5. Yes? So what choice you have for this one? Yes?
6 or greater.
6 or greater. So there is not unique, yes? Because if n is greater than, or if, can I choose 5?
No.
No, because if I choose 5, one possibility is that n is 5. Then 1 over 5 is not strictly less than 1 over 5. So I cannot choose 5. Yes? Can I choose 5.2? In principle, yes, because 1 over 5 over 2 is still, but I want a natural number. So this means that the number that I want to choose is, there are infinitely many choices, but I just need one of them. So you just introduce one. So for example, in this problem, you can say that, okay, let us take this 6. If n is greater than or equal to 6, this is guaranteed. if n is greater than or equal to 3, still this might happen, but it is not guaranteed. I want to choose it in a way that it guarantees this. Is that clear? Yes? Okay, now you have to do the same thing for any choice of epsilon, because here I am giving numbers for epsilon. 2, 1 over 5. But imagine someone gives you a typical epsilon without knowing exactly what that number is. What you know is just that is positive. Okay, can you come up with an intuition? So the point is that, can you choose this one? Can you choose this one so that it guarantees this one for any positive epsilon that I give you? So it means that I give you a positive epsilon, then I lose my control over epsilon. Yes? Then you have to do what? You have to fine-tune this n. I cannot change my mind in the middle. I have to think about an epsilon, I give it to you, I do not have any control over epsilon anymore, and I am waiting for you to give me a natural number that guarantees this for my epsilon. Yes?
Let n be the floor of 1 over epsilon plus 1.
It's very good. It's a very detailed one. You don't need, but if you write that, that's correct. So you would say that this is the floor of 1 over epsilon plus 1. Yes? So that will work. Actually, that is exactly what we are saying. If you write this is very good, but you don't have to suffer to really find the exact form of that n. Okay, instead, if I want to prove this, how should I prove this? I would say that, so you have given me an epsilon greater than 0, and I use Archimedean property to guarantee the existence, do you remember, a natural number such that 1 over that natural number is less than epsilon. So what you did, you actually find one of them. If you do that, that is completely okay, but you don't have to be very precise and find the exact formula for your n. You just need to guarantee the existence of such an n. Okay, so epsilon greater than 0, according to Archimedean property we saw earlier, the existence of a natural number with that property is guaranteed. Yes? And then, do you agree this n that I am looking for is this n guaranteed by Archimedean property? So do you see the logic? He actually proposed exact form of that natural number, which is correct. Okay? Here, if you ask me, well, like what that n is, I say I don't know. And I don't need to know. What I need is the existence of such an n. If I can prove to you such an n exists, I am done. So what I'm saying is that epsilon is greater than 0 by Archimedean property. You have to believe that this is true. Now I claim the same n that Archimedean property guarantees its existence. It will work for my n. Do you see that? Because if this is the case, and if n is greater than or equal to n, everyone agrees that 1 over n is less than or equal to 1 over n. Yes? And 1 over n is less than epsilon. So I achieved the goal. Is this logic clear? So what you did, what I'm saying is that, because in harder cases, coming up exactly with the form of the number is not that easy, and that would be just a waste of time. But if you just sit down and do it, of course that's correct. You propose the best one. But what I'm saying is that don't have this logic in mind because it makes life harder. So you just need to prove the existence of such a number. Of course, if you propose it exactly, you already proved the existence. Is that clear? Okay. So let epsilon be given. We prove that there is a natural number n such that this, whenever that happens, and then you write this one, so don't write this. This was good. If you write that, that's okay. But then I would say that epsilon is greater than 0 by Archimedean property. The existence of such an n is guaranteed. What that n is, I don't know, but the existence is guaranteed. And now I claim, if my term number is above this number guaranteed by Archimedean property with this property, I am done. And that's the proof. Is that right? So you have to write these words in the problem. Any questions? So you have to work a little bit. Sometimes these are tricky. So this one, I have changed the underlying set from the set of real numbers to the set of open interval from 0 to infinity. Okay, so what do I have? I have example 6.9. So the metric is the same, so everything is the same, but the set has changed. Okay, and then this distance is just, and my sequence is also the same. Okay, so this sequence was converged. This sequence converged to 0. That is the same sequence. Metric is the same. The underlying set has changed. Instead of considering the whole system real numbers, I have only from 0 to infinity. Now, I don't want to go through it in the detail. You can see my solution in the notes that I have uploaded. But what is your guess about this one? This is the same sequence. The set has changed. Can I say that this sequence is convergent? Yes. In the future, my solution to this problem is not based on future things. So you can read it, but because we don't have time, I want you to read it yourself. But later, we will prove that if a sequence converges to a point, that point is unique. Yes? In this problem, we prove that this sequence converges to 0. Okay? So if it converges to 0 in the set of R, it cannot converge to any other point. Okay? So it means that if I restrict my set to 0 to infinity, still, if this is going to be convergent under the same metric, then limit should be 0. But 0 is not in my metric space. So still, I can say that this is divergent. It is not convergent. It does not converge in this space. But in that space, if X is the whole R, it converges to 0. So the notion of convergence is not just you can find that number. This number, I have written it somewhere, hopefully, or not. Yes, you see, if there exists a P in your space. Okay? So even if you can find that number, but that number is not in your space, you say the sequence diverges, not converges. Okay? The next one, I have done the other way. So I'm doing some gymnastic with the same simple sequence. Okay? So what I have done, I have kept the sequence the same. You see the notes. A sub n is still 1 over n. I have kept the underlying set to be R again. So far, it is a carbon copy of that problem. So what I have changed the metric. I have changed my metric to the discrete metric. Okay, and we want to show that again, the sequence diverges. Okay, so let us see why. This is a good exercise to see. So 6.10, what do I have again? X is the whole R, but D is the discrete metric. You remember what was it? Discrete metric. The sequence is still the same. Okay, so discrete metric was dx and y is equal to what? 0 if x is equal to y, and 1 if x is not equal to y. Yes? So we want to show that, the sequence an diverges. I really want you to understand, this is extremely simple, but this type of arguments you need to learn, okay? Usually the proof is by contradiction. If you want to show that this does not converge, you say that, okay, let us assume that it converges and see what contradiction it will give us. Okay, so solution is this. So in this problem, try not to imagine how should I know this. This is the first example of this type that you are seeing, hopefully. And then you will learn this method. So you need to be patient to see why what I am writing eventually works. And then by doing more examples, you will probably, hopefully, learn how to do that yourself. Okay? So we say that, okay, for a contradiction, let AN converges to A. So where A is in R. So I want to prove for you that this does not converge. If you don't agree, let us imagine that this converges to a point in my set. A. What A is, I don't know. You told me that this converges, so I have to assume that is the sum A. Okay, but now this is the trick. I would say that so then if you say that AN converges to A, you can guarantee the existence of a natural number such that if n is greater than or equal to n, this implies what? This implies that the distance from your sequence, which in this case is 1 over n, minus that the number you proposed, I have to write d, because I am working with d. 1 over n and a is less than, this is the tricky part. For example, I choose it 1/2. First of all, don't resist, okay? I want you to see that what I have written is valid or not. Yes? Why? Because if you say it converges, for every epsilon, I can find that natural number, so it works. Now I have chosen that epsilon 1/2. You might wonder why 1/2. Don't think about that part yet. Try to understand that what I have written is valid. Because when you say AN converges to A, it means any positive epsilon that I give you, including 1/2, you can guarantee the existence of such an n that works in this case. Is that right? So the only thing you don't understand right now, why I haven't chosen any other number, I have chosen suddenly 1/2. You will see why. But I want to feel it to hear from you. So let us go here and understand this. D of 1 over n and A is supposed to be 1 over half. Okay, so can you tell me, remember, this is discrete metric. What does this mean? Yes?
This means that 1 over n is equal to A.
A. Do you agree? Because the discrete metric, the output of a discrete metric is either 0 or 1. If it becomes 1, 1 cannot be less than 1/2. So if this discrete metric is less than 1/2, it means these two numbers should be the same because there are no other options. Understandable? Okay, so this means 1 over n is equal to A. This is the translation, so you can keep it in a scratch paper. So this means that, by the way, this is the other way around as well. So these two are equivalent. If 1 over n is equal to A, the distance is 0 and 0 is less than 1/2. So this means that when two things are equivalent in mathematics, it means that you can take this off and put the other one instead. Is that right? So this means that, therefore, what happens? This claims that there exists a natural number such that if n is greater than or equal to n, no matter what n is, the only restriction is that you have to choose this n greater than or equal to this n. Do I know this n? No. I don't know more or less anything, okay? Implies, what should I write instead of that? But can you see the contradiction now?
Yeah, that's a problem because
It's a contradiction.
Yeah.
It tells you that there is an n, so that no matter what n you choose after that, 1 over n is equal to that fixed number A. This cannot happen. Do you see that? That's the contradiction. Because this tells me that, for example, let us say that this is 5. It means that 1 over 5 is A, 1 over 6 is A, 1 over 7 is A. This cannot happen. Yes? So this is the contradiction. And now you see why I have chosen 1/2. If I had chosen 2, do you think this will work? No, it doesn't work, but it doesn't mean I have a proof. It doesn't mean I have a contradiction. I don't have anything. So this means that, could I choose 1/3? Yes, if you choose 1/3, it will work. Could I choose 1 over 10? Yes, it will work. So it is not that much unique, but you have to think about what is coming next to fine-tune this a little bit so that your argument works. If the argument does not work, it doesn't mean I have the proof. It doesn't mean I have the contradiction. I have nothing. So I have to do something to go back and fix. Yes, please.
Can we say in the previous step that we know that it's not going to work because x is equal to y, so it's one specific point, but the definition said there had to be an infinite amount of points. But we know from the definition that if x is equal to y, then that's just one point and it's the only point that works.
Yes, somehow yes. But I like this one.
Yeah, that's
Yes. Okay. And so this means that what is the moral? What is the take-home lesson from here? It means convergence is something really depending on your underlying set. Yes, because you see, I have kept the sequence the same, the metric the same. I changed the space. Suddenly, convergent sequence became divergent. Here, I kept what the same. I kept the set the same. I kept the sequence the same, but I changed my metric. Suddenly it becomes divergent again. So the notion of convergence depends on the set and on the metric defined on the set. Is that right? Okay, good. So let us go to so I have written this remark here for you. So that's exactly, the previous example illustrates an important point. Convergence depends not only on the metric, but also on the ambient set in which the sequence is regarded. I have explained, okay? So now let us do a little bit more complicated example. By this epsilon delta and carry on. Okay, so this is what we want to do. Example 6.12. So a sequence is given to you, and a sub n is equal to 2n plus 1 divided by 3n plus 2. So you know in calculus they could have given you this and asked you what the limit is. So what the limit is?
2/3.
Yeah, because if n is extremely large, you can ignore 1, so it's 2n, and you can ignore 2, it's 3n, and you divide, it's 2/3. But here, I have given you the answer, okay? So, an is this one. The claim is that we want to prove that this converges to 2/3. So that is what we want to prove. Okay, so how do you write it? So, solution. So I will start with this sentence. I would say let epsilon greater than 0 be given. Okay? We prove that. What happens? There exists a natural number where in the set of natural numbers, so that if the number term, the term number n, little n, goes beyond that, it guarantees. Okay, can you fill it up for me? Because this is just the normal sequence in the Euclidean space. So instead of d, I have absolute value. So what should I write? Absolute value of what? My sequence, yes?
Minus 2/3.
So if you don't mind, let me write this, yes, instead of writing it in 2 steps. Less than?
Yeah, less than
Epsilon. So it means that I have given you my epsilon, and imagine that I am a little bit mentally sick, and if there is one epsilon doesn't work, I can just give you that epsilon. Okay? So you have to imagine like this is like a game. So I give you an epsilon. I do not have any control over that epsilon anymore. I am waiting for you to give me a natural number so that if this happens, it guarantees this happens. That is the logic you should have back in your head. But because this is a little bit complicated, usually people cannot guess the correct form of this n. And don't have this logic to find that n. If you can find it, that's okay. Okay? But you just need to prove the existence of such an n. So no one starts from here. I want to simplify this to understand the connection between this and this n. Because what I have in my hand is this little n. I want to control this little n by this capital N so that this works. Okay, so what I do, I will start from here. And try to simplify it as much as I can. Okay, so this becomes equal to, I take the common denominators. And then this will go here. This will go here. Yes? So this becomes absolute value of -1 divided by 9n plus 6. And hopefully you agree that it becomes 1 over 9n plus 6. Do you agree? Okay, so this means that instead of concentrating on this one, which is a little bit complicated, I will concentrate on what? I will concentrate, so instead of this one, I can write 1 over 9n plus 6 is less than epsilon. So now my question is reduced to this question. I want to guarantee the existence of this n such that n greater than or equal to n guarantees this one. So what I did nothing, I just simplified this algebraically. And instead of looking at a complicated problem, I am looking at a simpler problem. Okay? Again, of course, for example, one method is that usually people try to find n. For example, this is I do it in a scratch paper. So I would say 9n plus 6 is greater than 1 over epsilon, yes? And then I move this to the other side. And then I divide by 9. 6 over 9 is 2/3. Okay? So now I understand that in a scratch paper, I understand that if I want to do this, I want to fine-tune this n, so that instead of this one, I would write that. Okay? This is not hard to guess. You can even write it in words. You can say n can be any natural number greater than this combination, whatever it is. Do you agree? Because I want to fine-tune this so that when n becomes greater than that natural number, it is guaranteed that n becomes greater than this number for the epsilon that I gave you in the beginning. So you can just write it in words. N can be any natural number greater than this number, even if this number is not a natural number. So you can say it in words. But I want you to learn some techniques. For example, my goal is to make this one greater than 9. Sorry, less than epsilon. Do you see that this one is less than 1 over 9n itself? Okay, and then do you agree that this one itself is less than 1 over n? Yes? So, and then if I manage to make this less than epsilon, I achieve my goal. My goal is to make this one less than epsilon. I know. But because what I have here is less than 1 over n, if I manage to make 1 over n less than epsilon, automatically this one also becomes less than epsilon. Okay, so there is no unique way of answering this question in the exam. Might be one of you write it in the way that I told you, might be you do it like this and answer it simpler. So this technique I want you to learn. If the expression here is complicated and you cannot solve this inequality, because I could solve this inequality, it was simple. But if this inequality is hard, you can come up with these ideas, okay? Instead of making what you want is smaller than epsilon, first make this one is smaller than something simpler and make that one less than epsilon. It will guarantee your job, yes? So for example, can you tell me what n is by this calculation, not by this calculation? So I would say that n is a natural number greater than n, yes? So if I choose, if I make 1 over n less than epsilon, I am done. But I can make 1 over n less than epsilon by Archimedean property. Yes, again, okay, so what I can say n is any natural number greater than one over epsilon. Do you agree? Because if n is any natural number greater than 1 over epsilon, then 1 over n becomes less than epsilon. And I am done. Okay? Understandable? Yes?
Did you say the last sentence followed from the problem?
Pardon?
The last sentence.
So you see, okay, so let me write it like this. So here I want to guarantee the existence of, so my claim is that n is any natural number greater than 1 over epsilon. Okay? So then it means that if n is greater than 1 over epsilon, I want to guarantee for you that 1 over 9 plus 6 is less than epsilon. This is what I want to guarantee.
So the last sentence was just a claim.
Yes.
And then, okay.
No. So in principle, I claim something, I have to prove it.
Okay.
Yes.
But now we can miss some solutions,
Yes, you can miss.
and that's okay.
That's okay.
So we can say
So that the way that's what I'm fixing, that mentality.
Yeah.
That mentality you have, you want to find the best thing that doesn't miss any number. But that's not the problem. You are making life harder for yourself. So it means that if I can have time, sit down and calculate exact value for n, I'm not missing anything.
Yeah.
But we don't care because we want just to prove the existence. Yes? Yeah, you are right. For example, at the end, I have to guarantee this for you. I told you that n is a natural number, any natural number greater than 1 over epsilon. Now I am claiming that. Now I have to prove this for you, that if n is greater than or equal to this n, this is guaranteed. Why this is true? Because if n is greater than or equal to n, then it means that 1 over n is less than or equal to 1 over n, but n is greater than 1 over epsilon, so this is less than 1 over epsilon. So it means that by this choice, I was able to guarantee that this one is less than epsilon. But that is good enough, because if this one is less than epsilon, my expression is automatically less than epsilon. Is that right? Understandable? Okay, so let us start the break and then we continue after the break.